normalizing and for the invitation. So yeah, I will talk about the free energy of the dilute Bose gas at low temperatures, and this is a joint work with Florian Haberberger, who is a PhD student at LMU, Christian Heinzel, Phantom Nam. So it's a bit weird to do this talk in front of such an expert audience. So at first I will just tell you things that you will find boring, and near the end I will tell you things that maybe you didn't want to know, and hopefully in between you might find something which is interesting for you. So the setup is very easy. So we look at n bosons in a box of size L, okay, and we are looking at a fixed density regime, so n very large and n over L cube fixed or converging to rho. And we consider this Hamiltonian. So we have those n bosons, they have kinetic energy, each of them, and they interact through some pair potential V. I forgot to tell you, but you please, I don't have many slides, so interrupt me if something is unclear, if there's any complaint, or I don't know. And in this regime, we want to assess the properties of the system. I mean, I will tell you which properties, the obvious ones. In the dilute limit, when rho AQ, where rho is the density of the system, A is just the scattering length of V. I will tell you what it is, but just think of a hard core, and in that case, A is just the radius of the hard core. And in this regime, rho AQ that goes to 0, then there is this famous paper by Li Wong Yang, physics paper, when they assess the first eigenvalue of this Hamiltonian. So they have a formula for it that goes up to the third order. I just wrote the two first orders here. And usually the second order is called, or is known to be the Li Wong Yang correction. So to understand this first order, I mean, it's not so difficult. Proof is a bit more difficult maybe, but to understand it, it's okay. So if you want to naively apply perturbation theory to this Hamiltonian, you can just think of the kinetic operator to be the invert of 1. And then what you do, you just test against its first eigenfunction, so the constant 1. And then, so this guy vanishes, and then you compute the interaction. You get n minus 1 over 2 terms times the integral of v times 1 over L cubed, because you have to normalize the constant function. And this gives you integral of v times 4 times n. So you don't have the right constant, because here I claim it was 4 pi times a, but you have the right order. So by doing this, you see that you're not quite in the perturbative regime, because this fails. So actually you should be a bit more clever. And maybe I can just put this out. So if you consider a state of the form product of I, j, I different from j, of f x minus xj, and you plug it in as a test function of the system, you normalize it accordingly. And if you think of this as a perturbation of the constant function, so f goes to 1 at infinity, then you end up on this effective two-body problem. Right? So by translation invariant, or at least locally, you can just reduce the dimensionality and express everything in relative coordinates. So you have a problem on R3, and you see that if you plug in, I mean by doing a lot of approximations, this test function in this Hamiltonian or quadratic form, then you end up having n minus 1 over 2 times this thing, and then you can minimize over f. Okay, so if you take f to be 1, you end up with our first unsuccessful trial state. And then there's a better choice of f. So if you look at the kinetic energy, of course it wants f to be 1. If you look at the potential energy, it wants f to be 0 on the support of v, but there's an equilibrium. And if you minimize over it, then you can call this quantity 4 by a, that's your scattering energy. So this sort of heuristics tells you that you're in a regime where the potential is very large. So you're not really in a perturbative regime. Okay. So the upper bound for the first order was given straight away by Dyson, by some sort of ansatz like this. And the lower bound was given much later by Lieb and Ingersoll. But they managed to go back to the perturbative regime in a way that I will tell you later. So the second order, so this Lee-Wong-Yang correction, it's a bit more complicated. You see there is 128 and a square root pi, so it tells you that's not so easy to get. And this comes essentially from interactions of the low momenta excitations. So the 4 pi a rho tells you that you don't have a pure condensate, so you have modes which are not in the zero mode. And the high momenta modes, they are responsible for the first correction, and more or less, maybe it's I like to think that the low momenta modes, low momenta excitations are responsible for the Lee-Wong-Yang corrections. So this second correction was proven as an upper bound by Yao Yin, in the 2009. And more recently, there was a new proof, a bit easier by Bastich and Einstein in 21. And also recently, the lower bound was finally proven by Fournet and Solovej. So you might have thought that people would have stopped looking for this system, investigating this system, and no. So now people want to, we want to look at the next eigenvalues. It turns out in the Lee-Wong-Yang paper, there's already a formula for the next eigenvalues, or at least the difference of the next eigenvalues and the first one, so that's called the elementary spectrum. Okay, so it's given by this formula. So it's the sum over the modes of MP, so MP is the occupation number of the mode P, times the Bogoliubov dispersion relation. So this Bogoliubov dispersion relation is just E of P square root P4 plus 16 pi A rho P square. So it seems a bit barbaric, but essentially this is quadratic for large P. It's linear for the small p. Yeah. And this linearity is what Landau used to explain superfluidity. So it satisfies this scattering, this dispersion relation satisfies Landau criterion that the infimum over p of EP divided by p is positive. And in some other regime than this one, in the Gross-Pitelevsky regime, where the potential is a bit less big, so it's a perturbative regime, but not exactly, then this formula was proven by Bocato-Brennecke, Chenet-Neuenstein. Sorry. Okay. Actually, I can go to the next slide. So we cannot compute directly the eigenvalues, but we can try to do something a bit easier. We can compute the free energy. So that's our Hamiltonian. Okay. And the free energy, at least per unit volume, is defined as written here. So you look at minus t log of the partition function. You divide by L cube and you let n go to infinity, n over L cube go to rho. And the partition function is just a trace of exponential minus the Hamiltonian divided by t. Now if you take t equals 0, you go back to the ground state energy. But if t is positive, then this gives you information on the next eigenvalues. This depends on the low-lying eigenvalues for small t at least. So now if you follow the Lee-Wong-Yang formula, and if you use Bose-Einstein distribution formula, right, so if you Lee-Wong-Yang essentially tells you that your system H and L is given by some energy En plus up to some unitary transformation. So d gamma of E. Right, so d gamma of E is just the sum of E pi. Okay. So this is just. So if you remember your physics class, then you can actually compute the free energy of such a guy, and it's not so easy. It's not so difficult to see that it's given by this formula. So maybe I can even write it down. So this is just sum over EP and P. And now if you look at the trace exponential of Hn, at least within this approximation, you end up having sum over all the possible T of P minus P of T and T. And then if you sum, this is a geometric series, so this gives you some, sorry, there's a product probably. Trace, so this gives you the product of 1 over 1 minus exponential minus EP. Okay, now if you take the log, you end up with this sum, and that's your formula. And this is essentially what we proved as a lower bound. So with the people I cited before, and that's our assumption. So we take a L1 potential non-negative. It's radial. This is an annoying assumption. So we have to ask that it is non-increasing. And we consider temperatures T, for which this new guy, so the thermal correction, is of the order of the Lee-Wong-Yang correction. Okay, so this, if you put T to be rho A, you see that this is rho A to the 5 halves. This is essentially what you obtain if you distribute rho square A over square root of rho A cubed. Okay. And currently we are working on an upper bound with Florian Hammerberger, Christian Hensel, and Benjamin Stein. Are there any questions? Let's go on. So now words on previous works. So as I told you, I mean there are many works which are concerned with the zero temperature case, so the ground state energy. Again in the dilute limit. So those are the works I cited before, except two ones which are the ones by Britsky-Solovey, sorry, who essentially derived an optimal bound. So they have the right lower bound, but with the wrong constant. And there's also a more recent article of Robert Saringer and Chiara Bogato where they do the same thing, but by a technique which is closer to the Liebing-Wasson technique and closer to what we do. So for larger for positive temperature, there are actually two papers from Robert Saringer and Yin, where they respectively derive the lower and the upper bound, and they deal with much higher temperatures, so temperature of the order of the critical temperature, so the temperature for which, below which there is a BEC. You also can do like larger than this TC. And they derive this formula, so for large rho, for large T, so there is some exchange effect, and the formula is a bit different, but when T is small, and it goes back to what. And more recently, there was some works in the gross PTST regime, so this is a regime where the potential is a bit less big than in the thermodynamic limit. And so there are some works of Deutschert, Saringer, and Wasson, recently also Deutschert, Saringer, and Bogato, Deutschert, Stocker. So they also prove BEC on the torus or on trapped in the trapped case, and also in the grand canonical case. So they have a two-term expansion. I think this is an upper bound, right? Okay, and then there are many other works which are related closely or not so closely. So I took the other direction than Peter yesterday, so I just cited everyone. I hope you are happy. So maybe let me give you, let me start telling you something about the proof, or at least the intuition on how we prove this.
So before you do that, just a naive question. So then the Lee-Yang formula, you said it becomes visible for temperatures which are, sorry, I missed that information.
Yeah.
Okay.
Exactly.
Okay.
Otherwise it's smaller. I mean, that's the thermal.
So if it's higher than that, you don't.
We don't know. So, I mean, it's also because, I mean, it comes from the technique, and yeah, because you have an effective temperature when you localize into boxes, and then the technique fails to do.
Thanks.
Thanks for the question. Okay, so that's the formula we want to derive, all at the top. And so remember, we are in the thermodynamic limit. So when you say thermodynamic limit, it's an invitation to decompose the system into subsystems and to use the subadditivity of the energy or of the free energy. Okay, and this is essentially what Lieb and Iwason did. So they took, say, the ground state, and then they just looked at the quadratic form. They decomposed the system into smaller subsystems. And this is very clever because if you think of why the ansatz from the very beginning does not work, I mean just a constant function, is because you are not in the perturbative regime. So if you look at the first eigenvalue of the kinetic energy on the big box is of order 1 over L squared. Now if you look at the kinetic energy on the smaller box, it's of order 1 over little L squared, which is much bigger. So by localizing into smaller boxes, you get closer to the perturbative regime. Okay, so this is just, I mean, this formula just illustrates the subadditivity of the entropy. Let me say, there is a privileged or a very peculiar length scale, which is called the Bose-Petevsky length scale. So it's also called the healing length. So they say it's the length, the shortest length on which the wave function moves, but it's also the length for which the first, in the gap between the first and the second eigenvalue of the kinetic operator is of the same order as the interaction potential per particle. So 1. Okay, so if you localize into the Bose-Petevsky length scale is just 1 over square root rho A, or you can just write it in a more dimensional friendly way as A, which is the length, divided by 1 or square root rho A cube, which is dimensionless. If you localize your Hamiltonian into this box, then you can just, by scaling, reduce the problem to a box of side length 1. So just do a dilation. Then you obtain a 1 over L square in front of the Laplacian, which we can scale out. And then it will give you a new potential, which has the form L square V of L. And if you take L equals to N, and you go back to what many of you know, which is the Bose-Petevsky regime of scaling. So now, if you do this decomposition, if you think of, if you look at the energy that is given to you by the quadratic form, you decompose it, and the quadratic form which is associated, the operator which is associated to the quadratic form of domain H1 is the Neumann Laplacian. So it means that if you want to use this method, you have to understand this operator, where the Laplacian is the Neumann Laplacian. And that might be tricky. So again, this is what was done by Lee and Iwason, and they localized to length scales which are much shorter than the Bose-Petevsky length scale, for which the potential is you are much deeper into the perturbative regime, so the kinetic energy is much bigger. and you can just use the double inequality, for instance, which is what they do for your favorite perturbative theory. Now, if you want to get the second order, the Lewis correction, then it turns out that you have to understand the energy at length scales which are much bigger, not much, but much bigger than the gross-P length scale, which is the one on which the potential is not anymore a perturbation of the kinetic energy. And this is difficult in itself. So recently, Fournet-Solovej did it, but not by decomposing into boxes, but because dealing with the nominal Paschen is technique, but by some very clever styling technique. Okay. And here, what we want to do is to use the Lee-Lumberson approach and to decompose into boxes using the nominal Paschen. Okay, so now you understood that most of the analysis actually relies on understanding this Hamiltonian. So HNL tilde, so the tilde comes because I just multiply by L square. See what I had before, there was the L square now. You can just forget about it and we can have a tilde on Hamiltonian. And this guy again interpolates between the gross PTST when L is equal to N and the thermodynamic limit when E of L is equal to capital L. So this Hamiltonian was actually very well understood the periodic boundary condition case. There are two papers of Adhikari René-Kirstein and another one of René Caporelli-Tichlein. And actually also there is the upper one paper from Bastich and Kirstein that I mentioned earlier. And in this paper they compute the ground state energy and also the excitation spectrum. And it has this form. Right? So it's essentially, it looks essentially like the Lee-Wang-Yang formula, except that no, it's not rho, but it's those dimensionless. I mean, this n over L which appears and so on and so on. But it's essentially the same thing. And recently, this guy with Neumann boundary condition was investigated by Hirabokato and Rampas-Haringer, and they obtained optimal rate for the ground state energy of this guy. And here what I forgot to say also, much before, so in the paper of Lieb and Haringer and also it's reported in the book, it was known already that we have a condensation for length scales which are much bigger than the gross PTST length scale. So here this rho a cube is very small and it has a negative power in the exponential. So this tells you that you can consider length scales much bigger than the gross PTST length scales. And this is essentially what, I mean, the input we use to make all of the mechanisms in our system. And again, so this is what we do. We look at this Hamiltonian with Neumann boundary condition on large length scales and larger than the gross PTST. Let me tell you what happens in the periodic case, because this is very instructive to understand first what should be done in the, yes?
The height was n times n over L, not n over L to the power.
Because if you look at this guy, you test against 1. Right? Okay. You missed the right constant, but it's the right order. You get n square, integral of the potential, which is 1 over L. So, yeah. So all of the work that was done in the periodic case was very instructive to do the Neumann case, because we essentially do something similar, but we deal with the Neumann problem. In the periodic case, when the torus, you consider this operator, now you have to put the distance between xi and xj in the torus. So usually people sometimes don't put the distance, they just xi minus xj, and it's very confusing, but if you know, for you it's obvious, but so v again is the negative 1, but is supported. And you can write this guy in second quantization. Okay. And I think I will not explain the second quantization, but it's essentially those guys, they are like the elementary operators with which you write your matrices. So if you have A, which belongs to LH, you can see it as a big matrix, which is the sum of A, J, E, and J, where Aij is the guy with only zeros, but the 1 in the jth column, highest line. And now if you want to look at its quantization, so sum over AI, then you just consider sum over Aij, and now instead of Eij, you have those creation and initial operators that satisfy the CCRs. So it's just a nice way to rewrite your Hamiltonian and to be able to do computations. It turns out that the potential is very nice looking because you have conservation of momentum. So this is due from the fact that if you pick your initial v, and if you consider a v of the distance between 0 and x, then this is in fact the periodization of v. Right, so you have v on your box, and then you periodize it everywhere. If instead you have the Euclidean distance, then two particles might not see each other if they are, say, if you look at the figures, if they are here. Oh, sorry, here. And this guy, so if we denote it by V periodic, right, and if you compute its components in like the base of the basis of the Laplacian, it turns out that it preserves the momentum. So the sum of the momenta on the right has to be equal to the sum of the momenta on the left. Okay, and this tells you that this Hamiltonian has this nice expression here. Now let me tell you about the analysis, how we deal with, or how it has been dealt with this Hamiltonian. So you write it in second quantization. So here it should be VL, I'm sorry, it's a typo. And VL is just L squared V of L. And the first thing you do is a C number substitution. So this was done by Bogoliubov. And there is a very nice way to implement it, which was given in a paper of Levin, Safati, Solovej. And so this C number substitution tells you that essentially, since you know that the zero modes are occupied macroscopically, you can replace A0 and A dagger 0 by square root n. Right, so by square root or the square. The square A dagger 0 is 0, it's just a number of particles in its own sets. By doing this, you just break the conservation of particles, but it means that you look, there's a typo? No. It means that you look at this Hamiltonian acting on the Fock space of excitations. Okay. So you just count, I mean, you just identify which term has 1 A0, 1 A dagger 0, 2 A0, 1 A dagger 0, 0, etc., etc. And this gives you essentially 4 terms, which are linear, quadratic, cubic, and quartic, 25 terms, on creation and annihilation operators which are not concerned with the zero mode. And if you test this guy in the vacuum, it corresponds to just testing on the constant function. So you get back your v hat of 0, so the integral of v, and here everything vanishes. But again, you know it's not the most clever way. So one clever way was done by Bogoliubov, was to say, okay, well, this is, if I assume that A dagger is of order 1, then actually I can just truncate this expansion and throw in the bin Q3 and Q4, and it remains a quadratic operator, which I know how to diagonalize. And by doing so, you can obtain the leading order, the right leading order. Okay. And you can to go actually up to the Limourian order, but with the wrong constant. And this was done by the paper of Erdős Yao. Okay. And so the take-home message of what needs to be understood from that is that if you want to resolve the energy at the Limourian order, or at least at the second order production, then you need also to take care of this cubic term, Q3. Right, so you need to push the expansion further. And this was done in the paper of Yao and Yin. And so they did not do that, but this is what we do. But they just introduced some cubic correlations in this form, more or less. And they were able to recover the Limourian correction. This was also done in the Bose-Triay regime in the paper of Bose-Triay and Einstein, and also this one paper in the dilute regime, the dilute limit of Bose-Triay and Einstein. So, how do you introduce correlations? Well, there's an easy way, or it's computational, but it's easy. So, just conjugate by unitary. So, to find a unitary, just exponentiate the skew adjoint operator. So, T1 is our first unitary, and B1 is the skew adjoint operator. And then there is this DRL formula that allows you to compute the action of this unitary on observables. So if X is an observable, then you can put some parameter T in front of your B and just differentiate or integrate. And the first Taylor formula gives you this. So at first order, this is X. The second order is given by the commutator of X and B1 sandwiched by the same unitary with the parameter T. And you can actually go on forever. And this gives you some adjoint expansion. And so adjoint B1 of K is just X commuted K times with B1. Okay. I messed up the align environment. So the goal of this unitary is to renormalize the quadratic term. Right? So the quadratic term, it has some energy, but not yet in a scalar form. So at least algebraically, what this unitary operator does is that by commuting with the kinetic and the Q4, so the main term of the Hamiltonian, kills the Q3. It's here, more or less equal to 0. And then the second order of this expansion above will give you the missing energy in your expansion. So here there is some notational collision, so it should be n square over L. And to do that, so those two equations, essentially, they mimic the scattering problem that we saw at the very beginning. But they mimic it on the many-body level. So the first quadratic transform is chosen, I think we saw it in Emmanuel's talk. It's something similar here. As, it's cooked up with omega, where omega is the solution of the scattering equation. So before it was called F, but omega is just 1 minus F. This is why you get right inside. So you can actually, you have a unique choice of this, equivalent choice of this unitary transform. Okay. You can just take the scattering function on the whole space. You can also solve this equation on the torus if you work on the torus. This was done in the squares. And here also there is a typo. I don't know if you can spot it. It illustrates the confusion of the periodic setting. So there is not exactly equality. So what you obtain here is the periodized version of omega. But essentially, as for the potential, and that's the mistake that we managed to solve and it now works. Okay. So the problem with the Neumann boundary condition. So so if you try to use the scattering solution of the full space, of course you can define the dilatory. You can always define the dilatory, but you cannot use the GML formula because you won't be able to compute the commutator. So when you compute the commutator, here you essentially apply the Laplacian. If you compute the commutator with the Laplacian, you apply the Laplacian to omega, and you make appear 1/2 of v omega and so on. That kills the Q2. Now, if you do it here, it's wrong because this omega of x minus y does not satisfy the Neumann boundary condition for the two variables. So if you fix say, a variable x and you look at it as a function of y, if you want, you cannot apply the Neumann Laplacian with respect to y. So you can do something else. You can look at the other approach. You work on the torus with Neumann boundary conditions, and you try to solve this equation. The problem is that now, since v is not the periodized v for the Laplacian, for the Neumann Laplacian, for the Neumann boundary conditions, it does not commute with the Neumann momentum, if this means anything. So if you try to solve this equation, it will be terrible, at least in momentum space. You can do it in position space, and this is what Chiara and Robert did. But then it gets a bit tricky to have information on omega, on the scattering length. So one solution is to do like the periodization of the potential in the periodic case, but in a Neumann way. So if you remember what the Dirichlet Green function looks like in a half plane, what you do, you just add a virtual particle, which is the reflection of the particle with respect to the half plane, so that at the boundary it satisfies Dirichlet. The function is 0. While for the Neumann, it's the same except that you just add. And there's a plus instead of a minus because you want the derivative to be 0. So this is essentially what this picture represents. So what we do is that we take the scattering solution on the full space, and then we periodize it on this. We add reflections of the point, and it turns out that this guy is exactly what you want, which is, this guy has a nice decomposition. So if you denote by omega hat of t, the usual Fourier transform of omega, then if you also denote up the basis of your Neumann Laplacian, so those guys are cosines, so they are not funny, then you actually can show that you can express this guy into like this, and this goes very nicely with your quadratic unitary transform. Okay, so we go back to the quadratic unitary transform. Remember, we want to we exponentiate some skew adjoint operator, quadratic, and its goal is to kill or to extract in a scalar way the energy contained in Q2. Okay, so those are the same formulas as before, with a better aligned environment. So that's our kernel. And now you might complain if you know, if you encountered before the scattering solution. So this omega decays like 1 over x. So if you sum it over z cube, it's infinite. So you have to add some cutoff. Okay, and we put it at distance lambda. And anyway, it's very convenient because I told you before that the 4 pi a of the leading order is given by the high momenta excitations. So if you localize at small distances, you obtain high momenta. Okay? So now if you consider the equation which is satisfied by this omega times chi lambda, so the cutoff at distances lambda, you obtain a modified scattering equation with the right hand side. It actually looks very nice. Why? Because you have the 4 pi a over L, that's the scattering mass. And then you have this guy, which actually scales perfectly. It's lambda minus 3 W of lambda minus 1 for W, which you can conclude exactly what this is, and it integrates to 1. So what you do by doing this, if you've heard of those beta scaling between mean field and gross Pitayevsky, you're just replacing this gross Pitayevsky or this interaction potential by a softer one, so one which has less correlation. Okay. So by doing this, of course, you don't kill entirely the Q2, but you have a remainder which you can express in terms of this softer potential. Okay, and turns out, I mean, you can do this approximation. This is essentially like, I mean, this new quadratic term is essentially like 8 pi a n over L, so that's what you want to expect, times sum over the p smaller than lambda minus 1. So it's exactly what I told you. You renormalize the high momenta and you end up only with something that depends on the low momenta. So here there are probably some plus emission conjugate part which are missing. And this is often called, I mean, the quadratic Hamiltonian with this guy is called the Lee-Won-Yang Hamiltonian sometimes by some physicists. Okay, on the scalar side, you end up with your desired renormalization of the energy plus an error, which actually will contribute to the Lee-Won-Yang order. Okay, so now as I told you, there's still this cubic guy that you need to renormalize, but this is not very funny, so I might not say a lot. But one of the main problems is that if you are cubic in A and A daggers, every time you iterate the general formula, you gain some A or A dagger, and you might wonder if this expansion converges or makes any sense. So this was carried out by, I forgot to cite, I mean, in the Kospitevsky regime by in the Bocato-Brenekich-Line Fina-Tempo paper. And what we came up with NAM later was also to put a cutoff here in N+, and that makes things converge nicely. So if you manage to do your cubic transform, then actually you also renormalize the quadratic operator. So if you sorry, I hope it's not confusing, but let's go back to the first formula. So here, this is the initial Hamiltonian you obtain. And if you look at it, there's only v hat of 0 appearing. And what those renormalizations do is that they transform v hat of 0 by 4 pi a. So here, this was done by the first transformation. And at this level, the quadratic Hamiltonian, this was done by the cubic transformation. Okay. Sorry. Yes, so here we have our quadratic Hamiltonian with v hat of 0 replaced by 8 pi a. And now this guy is quadratic, so you know exactly how to diagonalize it. There's a nice theory.
Sorry, but with this TC, I mean, how many commutators do you have to take to get what you want?
2. Okay. So now, I mean, it depends if you want a lower bound or an upper bound, but for an upper bound, then I mean we finish off by some localization techniques also from Levin, Nam, Sarfati, Solovej, that essentially tells you that this approximation where you put the cutoff is valid. And we use the BEC result of Liebs-Haringer that tells you that you indeed have PEC for length scales which are much bigger than the gross PTFT1, but not so big neither. Okay. So now the system is essentially quadratic, so quasi-free. So you can diagonalize it, and you end up with exactly the formula that you expect. So first term of the constant energy, second term of the constant energy, the Bogoliubov Hamiltonian. And now we can use what I told you. If you manage to do that with Neumann, you can use Neumann bracketing and subadditivity of the free energy. And this is the FPOG, so that's this guy. This is essentially what you obtain if you compute the free energy of this guy, which is what I tried to do earlier. So you obtain a sum, okay, but you can make up here a Riemannian sum to obtain this nice looking integral, which was in the claim of the theorem earlier. So in summary, I think it's over. I mean, we look at the dilute regime, rho A cube goes to 0, and we derive generalization of the Lee-Wang formula at positive temperature. So we have this order rho A cube here with a parameter that depends on the temperature. On T equals to 0, we obtain again 128 over 15 square root 5. We work, I mean, all of the analysis reduces to considering a Hamiltonian on a large box with Neumann boundary conditions. And okay, as I told you, it's a new proof of it's another proof of the T equals 0 case. So thanks a lot.
Thanks a lot, Arnaud, for the very nice talk. Questions? I think I have one. So, I mean, how difficult is the step from the lower bound you get for the energy to the calculation of the free energy? I mean, I guess you make errors here, and then when you compute the free energy, does this make a?
So you mean the Neumann bracketing? Or?
Yeah. So I mean, you got right. So you got the Neumann bracketing for the system in the small box, and then from there you can compute the free energy of the whole system. How much do you have? I mean, how difficult it is that step? I mean,
well, it depends for whom. So,
you make in a small box, then you energy.
Well, I mean, so that's a good point. So I should have stressed that. So this is the main reason we have to consider boxes larger than the Gauss-Pitayevsky length scale. That's the length scale for which the pores are smaller than the Lee-Wang order.
Okay.
This is also why we don't have to look at higher temperatures because we cannot resolve anyway.
Okay.
That depends essentially on how large your boxes can be. But if you have large boxes, you're outside the perturbative regime. Then
so the restriction of the size of the box is from applying this result of Robert about condensation. That's
exactly.
The main restriction.
So not only. I mean, so we are focused on just considering boxes just bigger than the Gauss-Pitayevsky.
Yeah, no, but that's enough.
How much can we push? I don't know. So, I think it comes partly from this. I'm sure there are other reasons why you cannot.
For this length scale, the error that you get on the localized system, it goes beyond this Lee-Wang-Yang, and you also have lower order terms, or
No. We cannot have. We don't have the N2 kappa that you have.
Okay. For the periodic, it was possible to go up to order 1.
Actually, I think we can actually. No, I think we can. We can have so there's a log term in the Neumann setting.
Okay.
Florian was interested.
The log.
So essentially, when you look at
So it's lower than Lee-Wang-Yang, but it's Lee-Wang-Yang divided by log, or what is it?
It's essentially n to the 2 kappa in your language, log n.
I see. Okay.
And so this comes from the fact that if you consider it's the way around. If you consider this periodization, you look at what it kills, I mean, it will kill the potential, which is not Neumann. It's just the normal potential. It's not the periodized according to Neumann. So you will have remainder terms that contributes to some extent.
So because Triay, this is just log n. I mean, it's
Yes.
bigger than 1. Okay, it's bigger than.
But then if you periodize in a normal way
Then you-
potential, maybe there are no
zero.
terms.
Other questions? Does not seem to be the case, so let's thank Arnaud again.